Here go exponential functions. An exponential function with a base of a is a function of this form, where a and x are real numbers such that a is bigger than 0 and a is not 1. Here's an example of what an exponential function would look like. Y equals 2 to the x power. Things that grow exponentially, and this is an example of it here. You've got cell division, you've got bacteria growth, any type of things that grow by splitting. Think of it like this. You've got one bacteria. Let's say the thing splits in half and makes 2 bacteria. Well, what happens with the 2 new bacteria? Each of them are going to split in half, right, and make 2 new bacteria. Exponential growth is a very quick growth. This is a great lesson to deal with as we discuss Ebola and listen to Ebola on the news, is exponential growth. Because I'm sure that disease would probably spread exponentially as well. These 4 new bacteria grow into 8 because each of them split into 2, right? And then 16, 32, 64. And what started out as 1, here's the scary part. What started out as 1 bacteria over a course of 24 hours, even if it's split and each one divided into 2 after 1 hour. Let's say it took a whole hour for a single bacteria to grow into 2 bacteria. How many of you think there would be after 24 hours? This would be after 1 hour, right? This would be after 2 hours. This would be after 3 hours. Now, can we look at this y equals 2 to the x power? Is that not a model of what I just showed you? At the 0 point, when you start with 0, 2 to the 0 power, anybody remember what anything to the 0 power is? 1. At the 0 hour, you have 1. After 1 hour, 2 to the first power, you have 2. After 2 hours, 2 to the second power, you now have 4. Okay, now, and after 3 hours, 2 to the third power, I have 8. So after 24 hours, this f of x equals 2 to the x, after 24 hours, f of 24. Somebody's got a calculator, 2 to the 24th power, type that in for me. What started out as 1 and grew or doubled each hour, all of a sudden after 24 hours is turned into? Yeah, it's scary, right? Exponential growth is a very, very quick growth. Here's you another puzzle, something neat to think about. If I took a single penny, you've got a checkerboard, and I took a single penny and I placed it on the first square of that checkerboard, and on the second square I placed 2 pennies. On the third square I placed 4 pennies, and I'm going to double it. Each time I go to the next square, I'm going to double the amount of pennies that I had on the previous square. And I'm going to offer you something. I'm going to offer you either $1 million or the amount of money on that 64th square. Which one would you take? I took a single penny, placed it on the first square, 2 pennies, and each time I just doubled it. How many pennies are going to be on the last square? Right? Single penny on the first square, 0.1 to the first power. I've got to double that. Now, let's try to think of the actual equation here, and it is an exponential equation. There's a reason we can talk about this here. At the zero time, here's your actual equation. You got that single penny times 2 to the x power. On the first square, well, actually, no, it'd be x minus 1 power, I believe. Yeah, because on the first square, if you plug in that 1 minus 1 will be 0. You're not going to double it on the first square. Does that make sense? So I had to tack on that minus 1. But on the second square, you double it once, right? You take that on the second square, you're going to take that penny and you're going to multiply it by 2, which is second square, 2 minus 1. We good? On the third square, we're going to double it twice. On the fourth square, we're going to double it again. On the fifth square, you're going to double it again. So there are 64 total squares. So if you want to know how much money, here, I'll pull it up on my calculator. If you want to know how much money is going to be on that 64th square, again, here's your function. And we're going to know f of 64. How many pennies will I have on the 64th square? Here you go. If I can get it to turn on. Oops. We had a single penny, 0.01. And we're going to double it, so times 2, how many times? 63 times, right? Does everybody know what that E is? That's a scientific notation. That's 9.22337 times 10 to the 16th power, which means you've got to take that decimal and move it over 16 times. That's how many pennies you got. That's how many pennies will be on that 64th square. Doesn't seem right, does it? Which, if you want to know how much money that is, instead of moving it over 16 times, just move it for 14. That'd give it to you in dollars, because 100, of course, 100 pennies in a dollar. So if you take this decimal, move it over 14 times, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 of the 14, so just tack on about 5 more zeros, and that'll tell me how much money would be on that 64 square. So if I haven't got it across to you, exponential growth is a very quick growth. Okay, and that's what we're dealing with is exponential equations. There's lots more examples, and as we go through the chapter, you'll see some more examples of these exponential equations. This first part of the chapter is going to be review. It says, let f of x, g of x, and h of x equal these. Find f of, on this first problem, f of 3 halves. So if f of x is 4 to the x power, that is an exponential equation. We want to find f of 3 halves, which would be 4 to the 3 halves power. That's something we did back in, I believe, the first chapter we did, is raising something to a rational exponent. Whatever number, reminder, whatever number is on bottom is the radical that you're taking. This would be a second root of 4, and then whatever number is on the top is what you're going to raise it to. You have two options. You can do the radical first, or you can do the power first. I would always do the radical first, because then you're dealing with smaller numbers. Final answer? Good. Square root of 4 and then raise it to the third power. Any questions? So therefore, f to the 3 halves power is 8. Moving along. G to the third power. Here's your g of x function. So if g of x is 5 to the 2 minus x, then g of 3 would be 5 to the 2 minus 3, or 5 to the negative 1 power. When you're dealing with negative exponents, you need a fraction bar to make it positive. Put a fraction bar, bring it to the bottom. Anybody? 1/5. 0.2. Any questions there? And now let's do one with h. H of negative 2. If h of x is 1/3 to the x power, then h of negative 2 would be 1/3 to the negative 2 power. Josh, do you remember what to do when you have a fraction raised to a negative exponent? Good. So that would be 3 to the positive 2, or 9. Any questions on exponential functions there? And all three of those are exponential. You have examples, and we'll talk about them more as we go. You have examples of actually exponential growth and decay here. Just the same way that things can grow exponentially, it can also decay exponentially. Now let's look at graphs of exponential function. And honestly, if you think about it, you probably have an idea about kind of what a graph would look like. At the 0 hour, you're starting out, well, most of the time with 1 of something, and then it starts growing. And it starts growing slowly at first, and then it just kind of shoots up. F of x equals 2 to the x power. You can always graph these with a graphing calculator, but let's just go through and just remind you. If you wanted to make an XY table, if x were 0, anything to the 0 is 1. If x is 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. But we also like to graph with negatives as well. So let's throw a couple of negatives on there. As you start traveling to the left on that x-axis, you got 2 to the negative 1 power. And Austin just worked one while ago that had that negative exponent in there. Anytime you're dealing with a negative exponent, you need a fraction bar, bring it to the bottom. 2 to the negative 1 will be a half. 2 to the negative 2 would be a 4. 2 to the negative 3 would be an 8. Does anybody see an asymptote line there? 2 to the negative 4 would be a 16. 2 to the negative 5 would be 1/32. You're getting closer and closer and closer. Think about it. 1 over 16, 1 over 32, 1 over 64, 1 over 128, 1 over 10 million. You're getting, as you're traveling to the left, you're getting really, really, really close to what? 0. 1 out of a trillion. Remember what we said before, when you divide a number by huge numbers, you end up getting 0. Here's an exponential function. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the second is 4. So you're growing exponentially, and that thing shoots nearly straight up. But as you go to the left, you're getting closer and closer and closer and closer to 0. Okay. That's an example of, and we'll go ahead and talk about it as we go, that's an example of exponential growth. As you're traveling from left to right, this thing is growing exponentially, like bacteria and disease. Y equals 1/2 to the x power. This is an example of an exponential decay. Let me show you why. Do that same t-table, and look what happens as your x values get bigger. And let's start with -2, -1, 0, 1, 2, and 3. Let's start with 0 here. Anything to the 0 power is 1. 1/2 to the first power is 1/2, but 1/2 to the second power, you're doing 1/2 times 1/2, or you can raise the 1 to the second and the 2 to the second. We know that property. That'll be a 4th. 1/2 to the third power is an 1/8. Do you see that this is actually identical to the one we just did, except for it's kind of flipped over the y-axis? So you have an 1/8, a 16th, a 32nd. So it's actually shrinking from left to right. 1/2 to the -1. Anytime you raise a fraction to a negative power, you got to flip it. That'd be the same thing as 2 to the first. 1/2 to the -2 would be 2 to the second. So again, you have the identical graph just flipped. It's symmetrical. It's symmetrical with 2 to the x across that y-axis there. Any questions? That's an example of, and they've got them both graphed there. This would be an example of exponential decay. Notice it doesn't ever fully decay. Same thing with carbon-14. We'll talk about carbon-14 dating here in just a little while. Carbon-14 dating is an example of exponential decay. The older something gets, the more its carbon decays, and that's how they try to predict how old something is, by seeing how much carbon. Well, when does it all decay? It's still there. It's still got carbon. If it's 10 million years old, it still has some of that carbon-14 left. And the last one of these, 3 to the -x power. I hope we didn't forget all that transformation stuff, because we're doing it again here. Wouldn't this, if you took that negative away, 3 to the x power, that's an example of exponential growth. 3 to the x power, that's 3 to the first, 3 to the second. Just think about it, it's actually growing faster than 2 to the x power. It's got a faster rate there. So what's the relationship between 3 to the x and 3 to the -x? We'll discuss it more later, remind you more about this later, but anytime you make an x negative, anytime you put a negative on an x, or you put a negative on anything, what does it do? Does it, what was our 3 transformation? Does it translate? Does it rotate? Does it reflect? It's a reflection, and it is a horizontal reflection. So if you've got an exponential growth and you reflect it horizontally, then this would be an exponential decay. 3 to the -x, actually, and I'm not going to go through the t-table, I just want to show you this. 3 to the -x, if you put a bar under that, brought it to the bottom, that's 1 over 3 to the +x, which if you want to get real technical about it, you could actually write as 1 over 3 all to the x power. For this reason. Could I put that same x on that 1? What's 1 to the x power? It's still always just 1. Does that make sense? 1 to the millionth power is still 1. So if you want to put an x there, it doesn't matter. So 1 over x and 3, or excuse me, 1 to the x and 3 to the x, we could write collectively as 1 over 3 all to the x power. Because again, it doesn't matter how many times you raise 1 to the x power, it's still going to stay 1. So 1/3 to the x power, that is an example of exponential decay. And you see there, it would be the flip of 3 to the x power. Any questions? Graphing recap. Well, we will go over this. A function is increasing if your a value is greater than 0, and your a value is what you're raising to the exponents. So if you've got greater than 1, not greater than 0. So if you've got like 2 to the x, that's going to be an increasing function. That's going to be something like that. If you have an a value that is less, 1/2 to the x power, that's going to be a decreasing function, exponential decay, because you're taking half of it each time. The y-intercept of a graph is going to be 0, 1, unless you apply some other transformation to it, unless you stretch it vertically. The graph has the x-axis as a horizontal asymptote. It's never going to cross it. Okay? The ones that we just discussed. The domain is negative to positive infinity, and the range is from 0 to infinity. It starts at 0 and it goes up. This kind of goes hand in hand with that. And the function is 1 to 1. I don't know if anybody noticed that. Reminder, a 1 to 1 function, each x has a single y, each y has a single x. It passes the horizontal line test and it passes the vertical line test. It's 1 to 1. Transformations, and then we'll stop for today. Reminder, pluses and minuses. When you add or subtract values, what transformation is that? It's a translation. When you add or subtract numbers, do a +3, do a -4. When you add or subtract numbers, it translates your graph. And a reminder that when you add or subtract something to just the x, as with this problem, it does backwards what you would think it would do. A -3 actually moves it to the right 3. Now, if you add or subtract something to the end, that's when it's happening vertically. Okay, so you've got to look: is it on my x or is it tacked on the end? So pluses and minuses translate. Multiplication and division. Remember what those did? If I took this whole thing and put ×3 out front, what's that going to do? Stretch. It's either going to be a stretch or a shrink, all depending on how big the number is, if it's a fraction less than 1, or if it's a whole number greater than 1. And then the last one, negatives. Negatives what? Flip it. And again, it all depends on where the negative is located. If a negative is located with the x, if a negative was up there in the power, it would flip it left and right. If the negative was located out front, it's going to flip it up and down. So that's all three of your transformations that we discussed. We didn't do rotations. I threw in rotations a while ago. Rotations involve matrices. We're not going there. But here we go. Your first translation that we're going to discuss here, y equals 2 to the x minus 3 power. Now, you've got to be careful with the parent function here. Before, we could just take all the numbers away. Well, sometimes. Y equals x squared was a different one, right? Y equals x squared, you didn't take the squared away. Here, if you want to know what your parent function is, take away any plus and minuses, take away any multiplications, take away any negatives. Your parent function is y equals 2 to the x power. And we graphed that a while ago. This would be an identical graph with the exception of this right here. That -3. Notice it's with the x. That x is up in an exponent, and there's a -3 with the x. Pluses and minuses shift your graph left, right. And in this case, since it's a -3, it's going to shift it where? Good. Shift it right. There's the two graphs. You have y equals 2 to the x power. No longer do you have y intercept of 0, 1 because you shifted it to the right. And there's your new graph. Shifted it right 3. What used to be at 0, 1 is now at 3, 1. Any questions? You got more stuff going on here. And if you want to, you're more comfortable with, instead of -4 plus, you're used to seeing that -4 at the end. Your parent function here is y equals 3 to the x. You have two transformations happening. You have that +2, and you have a -4. Canada, the +2 is located with the x. So is it going to shift it up and down or left and right since it's with the x, Canada? Where's the x values located? Left and right or up and down? Left or right. Good. So that +2 is going to shift it either left or right. Anytime it's located with the x, it's backwards from what you would think. So that +2 right here is actually going to shift it left 2. And then you've got this -4 tacked on the end. It's not backwards. It does exactly what you would think it is. If it's a negative, it's going to go down. If it's positive, it's going to go up. So that's going to go down 4. So you've got your basic y equals 3 to the x power, which here's the graph of it. Y equals 3 to the x. But what used to be at 0, 1 is now shifted left 2 and down 4. And it's now located at -2, -3. Same graph, though. Any questions? Nearly done. Here you have 3 transformations happening. Your parent function, take away the negatives, multiplication, take away the negative up in the exponent. Your parent function here is y equals 3 to the x. Again, it's the exact same graph we just looked at. That's an example of exponential growth, but once you throw all these negatives in there, it might change a little bit. Actually, it changes it a lot. See if you can tell me, Jason, what about this negative? What's it going to do? Good. Flip it across the... Flips it left to right, so it's actually flipping it across the y. Good. Now this one flips it across x. So you got flipping it across the x-axis, flipping it across the y-axis, and the very last thing, that's a fraction bar, the 1/2. Ask yourself, is the 1/2 up in the exponent with the x? No. So since it's not located on the x, then it happens vertically. That's the test. If it's up here with the x, it's going to happen horizontally. If it's not with the x, it's happening vertically. So 1/2. Next question is, does it stretch it or does it shrink it? Because sometimes a 1/2, if a 1/2 was up here, it would actually stretch it because you have to flip it over. Do you flip it down here? Nope. So that's going to compress. Again, since it's not with the x, it's going to happen vertically times a 1/2. So it's going to make it half as tall. We'll make it short and chunky. Here's your transformations. Here was, well, they didn't show 3 to the x. If you want to start with 3 to the x, it would look like this. So there's 3 to the x, and then when you did the 3 to the negative x, it flipped it over here. Then when you tacked on that negative 1/2, it shrunk it, made it shorter, and it flipped it down here. So there's an example of y equals negative 1/2 to the 3 times 3 to the negative x. By the way, reminder, high school RV, that's the order things are done in. Horizontal translations, stretches and shrinks. So you would actually, in this problem, done stretches and shrinks first. Reflections happen third step, and then vertical translations last.